before we go into today's lecture, let's look at what we did in lecture number 22, the last one. So in the last one, we were following up on Einstein-Podolsky-Rosen's this wave function, two-particle wave function they had constructed, which was highly correlated in momentum. That means here we have a superposition of two-particle wave function, and what we find that in this wave function, if the first particle is detected with momentum p, second particle is guaranteed to be detected with momentum minus p. Of course, they can have any p value, but once the first particle is detected with momentum p, second one is guaranteed to be detected with momentum p. Now, the same wave function can be written in the position basis in this manner, and the interpretation that we get here is that if the first particle has position x, the second particle is guaranteed to have position x plus x naught. So, they are correlated in momentum as well as in position, and we also see that this wave function, this two particle wave function cannot be written as a product of two single particle wave functions. That means cannot be written as the product of the wave function of the first particle times the wave function of the second particle. So, this simultaneous correlation in position and momentum basis, this can actually be written in terms of this inequality, conditional Heisenberg uncertainty relation, and we see that this can actually indeed be less than h bar by 2. So, this conditional uncertainty can actually violate Heisenberg's uncertainty relation. So, these arguments that were put forward by Einstein, Podolsky and Rosen to show that the quantum mechanics is incomplete, these very arguments are now known as entanglement in, for example, this was given in position momentum. So, these arguments are known as entanglement, and here it is entanglement in position and momentum. So, what entanglement means is basically simultaneous correlations in two conjugate variables or non-commuting operators, and the inseparability of the two particle wave function or state into individual particle states. So, again the arguments that Einstein, Podolsky, Rosen put forward to show the inconsistency, those very arguments are now called entanglement. So, we can have entanglement in position momentum, we can have entanglement in time and energy, we can have entanglement in angle and orbital angular momentum, and so on. And these are all continuous variable, infinite dimensional. We can also have entanglement in two dimensional variable, and we saw that we can have this state psi equal to 1 over root 2 HH plus BB. This is the state written in the horizontal vertical polarization basis, and the interpretation here is if the first particle is H, second one is guaranteed to be horizontally polarized. If the first particle is vertically polarized, second one is guaranteed to be vertically polarized. Now, this very same state that is written here in the horizontal vertical polarization basis can also be written in the 45 minus 45 basis, and it looks then like this. And so, now what we see is that if the first particle is found to be 45 degree polarized, and the second one is guaranteed to be 45 degree polarized. At the same time, if the first particle is found to be minus 45 degree polarized, the second one is guaranteed to be minus 45 degree polarized. So, we see simultaneous correlation in HV basis as well as in 45 minus 45 basis. And of course, this wave function, this two particle state cannot be written as a product of the state of the first particle times the state of the second particle. So, we do see simultaneous correlation in two conjugate bases and inseparability of wave function, and this is then referred to as polarization entanglement. Of course, we can't have an uncertainty relation like this here, but the two aspects that define entanglement, which is simultaneous correlation in two conjugate variables and the inseparability of the two particle wave function or state, that is there here as well. So, that is the polarization entanglement. So, we also looked at a few particular measurement outcomes, and that which can be explained by quantum theory, but not by hidden variable theory. And this outcome was that suppose in an experiment one has two particles coming in, and one measures these the polarization of those two particles into different bases, and then the experimenter finds that if the single photon is horizontally polarized, idler is also horizontally polarized, and whenever it is vertically polarized, idler is vertically polarized. That means correlation in HV basis. At the same time, if the signal photon is measured to be 45 degree polarized, idler is 45, signal is minus 40, idler is minus 45. So, a perfect correlation in both horizontal vertical and 45 minus 45 basis. And the question is, can quantum mechanics produce such a result? And the answer is yes. If we have such a wave function, quantum mechanical wave function, that can actually reproduce this measurement outcome. but can two independent sources also produce such correlation? This is two independent sources. This is the requirement for hidden variable theories, and the answer is an emphatic no, that yes, such sources cannot produce these results. And this we argued to show that the hidden variable interpretation of quantum mechanics is actually not possible, and that hidden variable theories cannot replace quantum mechanics. But but in this lecture we show the derivation, the results, the mathematically rigorous proof that was done by John Bell to show that indeed the hidden variable theories cannot replace quantum mechanics. So this was the work done by John S. Bell in 1964, in which he rigorously showed that the hidden variable theories cannot replace quantum mechanics. So here is the proof for that. So let's just consider this two particle system. There is a source of two photon or two particle. We don't know at this point whether it is entangled or not entangled. So it's just two photons, two particles coming in. And we will use the same source to analyze what we can get with hidden variable theories and what we can get with quantum mechanics. So just a source of two photons here. And there is a detector here that detects these photons. There is a detector here that detects the second photon. And we then consider this A and B to be dichotomic variables. That means A can be plus minus 1 or B can be plus minus 1. Now these thetas, these are the polarizers or polarizing beam splitter. So the polarizer kept at an angle of theta 1. So if the polarizer is kept at an angle of theta 1, then if it's a light that is polarized along theta 1 direction, then of course it will just pass through it. But light that is not polarized along that light that is polarized at 90 degree to theta 1, that will go in this direction. But if we have a light polarized in some other direction, not theta 1, then it has a finite probability of going this way as well as that way. So whatever is the polarization of light coming in, if it goes this way, when the polarizer is kept at an angle of theta 1, if it goes this way, then we call that A has a value 1. But if it goes this way, then we call the parameter A or the variable A has value minus 1. Similarly, if the photon here passes through this polarizer kept at theta 2, then we assign plus 1 to B. And if it doesn't pass through this polarizer or it goes to the other port, either it gets absorbed in experiment or it goes to the other port, then we assign a value minus 1 to B. So these are the dichotomic variables. So that's the experiment. Okay, now for this experiment, let's define a correlation between these two variables. It's a simple correlation A theta 1 times B theta 2 ensemble average. So we put a polarizer at theta 1, put a polarizer at theta 2, and then we do a lot of measurements. And in each measurement, of course, A can only take plus minus 1, B can only take plus minus 2. Hence, A times B can only be either plus 1 or minus 1. But then we take a lot of measurements, and depending on how those different measurements are, the ensemble average can be anything between 1 and minus 1. It could be less than 1 because we are doing an ensemble average here. So that's a simple correlation quantity that one constructs here. Now within the hidden variable model, this correlation can actually be written like this. So this this is an ensemble average, and anytime we have an average, the way we define it is the average, the quantity itself times the probability density, and then integrated over. Now here we are introducing a variable lambda. This is called a hidden variable. So this variable, we just don't know what that is, what is the value of it, what decides the distribution of it. But these are allowed within the theory, and the values of A and B, they are actually influenced by the value of lambda. Although it's hidden variable, although it is hidden, we don't know what it is. In fact, this lambda doesn't represent just one hidden variable. It could actually also be a set of hidden variables. Then there is a distribution of this hidden variable, and then for that is given by this probability density, and for a given lambda, the value of A and B, they actually depend on this lambda. So that is the average, the definition of average that we will use in this case. Of course, this rho lambda d lambda has to be equal to 1. Okay, now here we note that the A theta 1 lambda, that means the value of A theta 1 when the hidden variable is lambda, that depends only on theta 1. Of course, it doesn't depend on theta 2. Anything we do here does nothing to the value that we get over here. Similarly, the B theta 2 lambda doesn't depend on theta 1 and depends only on theta 2. Therefore, any measurement we do here doesn't have any effect on the measurements done over there. So this is making the locality assumption. So the locality assumption is intact here, and this is done specifically to just avoid those situations that we had in the Einstein-Podolsky-Rosen argument, in which it turns out that doing something on the first particle decides the wave function that the second particle would actually take. So just to make sure that those non-locality interpretations that the hidden variable theory actually wants to get rid of, and that's why there is a strict locality condition or assumption being put here. So now that the locality assumption is intact, now we can proceed further. Now this is the correlation. Now let's consider this quantity, which is c theta 1 minus c theta 1 theta 2 minus c theta 1 theta 2 prime. So this theta 1 and theta 1 is the same, but we have theta 2 and theta 2 prime for the second variable. So now this quantity and the absolute magnitude of that. So this quantity is simply the magnitude, and then we have a theta 1 lambda, b theta 2 lambda, and then rho lambda d lambda. Of course, since a theta 1 lambda is constant for this, we take it out, and then we have b theta 2 lambda minus b theta 2 prime lambda. Just constructing this quantity, we have it for this. Now this quantity, which is the absolute value of this quantity, this definitely will be less than or equal to this one, where we bring in this modulus inside the integral and take the modulus of this quantity instead of the whole integral. So this will of course be less than or equal to this one. Now we know that the value a can only take or the magnitude of a is 1, because a can only take plus minus 1. So the magnitude of a is 1. Hence this quantity, where we have this a and b theta 2 and b theta 2 prime, so this quantity will definitely be less than or equal to b theta 2 minus lambda minus b theta 2 prime minus lambda. So it's basically this whole quantity with a being put as 1. So this will be less than or equal to this quantity. So this correlation quantity that we consider, we can this will be less than or equal to this. So now we can similarly have another such quantity. Now in this case we have theta 1 prime theta 2 and theta 1 prime theta 2 prime. There's a minus and there's a plus. So just like c theta 1 theta 2 minus c theta 1 theta 2 prime was b theta 2 lambda minus b theta 2 prime lambda, since this is plus here, we will also have a plus over here. Now if we add these two, this plus this, then what we get, that this plus this is less than, since this is less than equal to this is less than equal to this, of course the addition is less than equal to this quantity. So this is what we have. Again, this is just a quantity we have constructed, and it will be clear in a moment as to why John Bell is doing it. Because if a theory, for any quantity, if a theory fails, that means that the theory actually fails. So that's the quantity we have. Now let's look at this. So here we have b theta 2 lambda and b theta 2 prime lambda, and here we have b theta 2 lambda plus b theta 2 prime lambda. So same quantity, b theta 2 prime, b theta 2 prime. Here is a minus, here is a plus. Now we know that the b theta 2 or theta 2 prime can only take values plus minus 1. So this is plus 1, this is either plus minus 1, plus minus 1, plus minus 1, plus minus 1, and then we have this absolute values here. So either this one is 0 and this one is 2, or this one is 2 or this one is 0. So that's why this quantity, the thing inside, this will be always equal to 2, because either this is 2 and this is 0, or this is 0 and this one is 2. Hence this quantity is basically equal to 2. So if this quantity is 2, and we also have that rho lambda d lambda, that is the distribution of the hidden variable, of course has to equal to 1. That means this quantity, which is this integral, and we have 2, and this can be normalized. So basically this quantity is less than or equal to 2. So we find that this c theta 1 theta 2 minus c theta 1 theta 2 prime plus c theta 1 prime theta 2 plus c theta 1 prime theta 2, that we had constructed is less than or equal to 2. That means in no experimental situation we can find that this quantity is more than equal to 2. This quantity is called S, represented as S, and it's called the Bell parameter. And this inequality that we have this one is called the Bell's inequality. So this was the inequality derived, and then Bell, through this, derivation Bell basically shows that the Bell parameter for hidden variable has to be less than or equal to 2. This cannot be greater than 2, and this is called the Bell's inequality. Now let's see what this Bell parameter can be, what is the maximum value one can get for the quantum theories. So again, it's the same experimental setup over here. It's just the source of 2 photons that's there, and then we are going to be doing these measurements with these dichotomic variables, but this time we will treat the experimental results using quantum theory. So okay, we have this quantity that we have defined, this correlation. Again, now for this quantum theory, how do we write this correlation? This time we don't have any hidden variable. So how do we write this correlation? So this correlation, which is A times B, and that's its average. So what are the values of A times B? The A times B we can have either +1 or we can have -1. So it's the value +1 times the probability of getting that value +1 plus the value -1 times the probability of getting that value -1. So these are the two possibilities we have here. What is the probability that we get a +1? So we can get +1 if we detect a photon at θ1. That means if the photon goes through this and the second photon goes through that. So there we can get a +1 here, +1 here, and that way we can get +1. There's one more way we can get +1 here, is that the first photon goes in this direction. That means it doesn't pass through the polarizer, and the second one also doesn't pass through the polarizer, and in that case we can get a -1 here, -1 here, and that will give us a +1 here. So these are the two probabilities that will give us a +1. Similarly, there are two other possibilities, one in which the first photon goes this way, second one goes that way, and then the first one goes that way and the second one goes that way. In these two possibilities, the product of A and B will be -1, and that's what we have it over here. So C θ1 θ2 is basically the sum of these four probabilities. This is just these two are the probabilities of the photon going either both passing through the polarizer or not passing through the polarizer, and these two are the probabilities that one photon passes through the polarizer and other one does not. So, and of course we have this -1 here, because here we have the value of A and B in these probabilities are basically -1. So this here in the case of quantum theory we have these four possibilities, but this way of calculating the probability is basically the average is same as what we did in the case of a hidden variable. It is just that in the hidden variable we have infinite number of possibilities, and that's why we have to have a probability density. But in this case there are only two possible values of A and B, and then correspondingly the four ways in which those two values can be obtained. So that's why we are writing the probabilities like this, but these two are pretty much the same way of calculating the average. Okay, now this probability that a first particle goes through the polarizer and the second one also goes through the polarizer, that we can just write θ1 θ2 here, although we have written plus here, and this one where the symbol we are using θ1 minus θ2 minus, just to indicate that the first one does not go through the polarizer, second one does not go through the polarizer. This we can also write as the probability that the first one at π/2 to the first polarizer, and second one goes again at the π/2 to the second polarizer. So this is just a different notations of writing the same thing. So similarly for P minus θ1 plus θ2 we can write as P θ1 plus π/2 and θ2. That means the first photon is detected here at π/2 to the polarizer angle, and the second one of course goes through the polarizer, and here first one goes through the polarizer, but the second one goes at π/2 to the polarizer direction. So these are the four probabilities we have, and if we use this we can actually get this correlation function. Okay, now how do we calculate these probabilities? So quantum mechanically we know that the probability of detecting two photons, so this probability is basically probability of detecting one photon at θ1 and second one at θ2. This one is a probability of detecting two photons, first one at θ1 plus π/2 and second one at θ2 plus π/2 and so on. So how do we define this probability? So this we have seen that this probability, such probabilities we also call coincidence probability. This is defined as this quantity where psi is a two photon wave function, and A1 and A2, these are the annihilation operators. So this A1 theta 1, this is annihilation operator corresponding to annihilating a photon at theta 1. Similarly, A2 theta 2 is an annihilation operator that annihilates a photon at angle theta, polarization angle theta 2. Okay, so now what is psi? So we'll assume that the entangled state that we have is of this one 1 over root 2 HH plus VB, although we can take any other entangled state, but at least in this example we'll just take HH plus VB as the entangled state. Now what about this A1 theta 1, the electric field operator? Now we know that this is the horizontal vertical and that's the theta 1 direction, and we know the modal decomposition works pretty much the same as the classical one. So this A1 theta 1, the annihilation operator in the theta 1 direction, this we can write as A1 the H cosine theta and A1 V sine theta. That means the annihilation operator in the horizontal direction, and this A1 V is the annihilation operator of a photon in the vertical direction, and this annihilation operator in the theta 1 direction we can write in terms of H and V. So this should be actually theta 1 and theta 1 over here, because we are using theta 1 over there. Okay, so that's the electric field operator A1 theta 1. Similarly, we can have A2 theta 2 as A2H cosine, this would be theta 2, A2V sine theta 2. Okay, so now using this wave function and these two electric field operator expressions, we can show, this can be shown, this is a simple math that can be derived, that this P theta 1 theta 2 with these values is basically half cosine squared theta 1 minus theta 2. So that's calculating just this term. Similarly, we can calculate these other three terms, and then we can show that the C theta 1 theta 2, the first one we have already shown, cosine squared theta 1 minus theta 2. This second one, this can be also shown to be half cosine squared theta 1 minus theta 2. The third one is sine squared theta 1 minus theta 2, and the fourth one is also sine squared theta 1 minus theta 2. So if we just put them all together, this is basically cosine 2 theta 1 minus theta 2. So that's the quantity we have. Again, this expression is for this particular entangled state. Okay, so now if we consider theta 1 to be 0, theta 2 to be 3 pi by 8, theta 1 prime to be minus pi by 4, and theta 2 prime to be pi by 8. I mean, this is just a set of values for theta 1, theta 2, theta 1 prime and theta 2 prime. For this value, we find that the Bell parameter, which is theta 1, theta 2, theta 1, theta 2 prime, theta 1 prime, theta 2, and theta 1 prime, theta 2 prime, this quantity, and here we have derived the expression we have derived only for C theta 1, theta 2. So we can have very similar expressions for theta 1, this C theta 1, theta 2 prime, and so on. And if you use this set of parameters, we find that the Bell parameter is actually 2 root 2. And of course, this is greater than 2. So the whole point here was that we take up an entangled state, and we show here we show that for at least a set of these theta values, we find that this Bell parameter that can actually be greater than 2. What Bell derived, Bell's inequality, what it was shown that this parameter for the hidden variables can never be greater than 2, but it turns out that for quantum theory, this parameter can indeed be greater than 2, although for a certain set of parameters. If we take some other values of this set of these theta values, then S may not be greater than 2 for all those set of values, but here is at least one set where we find that the value is definitely greater than 2. So it violates the Bell inequality. Of course, there can be infinite number of set of theta values at which the Bell parameter can be greater than 2. So this was a very definitive proof that Bell constructed a quantity, and he shows that the hidden variable theories, no matter how it is constructed, how the distribution of the hidden variables are assumed, this Bell parameter can never be greater than 2. But for quantum mechanics, we can find situations, for example, this state and this set of theta values, so we can find situation where this parameter can be greater than 2. So this was a very definitive proof. So now the thing was, if one could show a violation of Bell inequality in an experiment, then that would show that there cannot be hidden variable interpretations. Of course, then one would have to use the quantum mechanical theories and quantum mechanical descriptions. So then there was a lot of effort to actually do that. So this was in 1964. So this was very definitive statements that was made that the Bell parameter less than or equal to 2 for hidden variable theories. but the Bell parameter could be greater than 2 for quantum mechanics, and the maximum value it can obtain is 2 root 2. So if in experiment, if one could show the Bell parameter is actually more than 2, then that shows that yes, one cannot have hidden variable interpretations. And this would act as an entanglement verification that yes, entanglement does exist. That means the feature that Einstein, Podolsky and Rosenberg pointing out that does exist within the theory. So this was the kind of state that was considered for the example. Here it was in the horizontal vertical basis, and this is in the 45 minus 45 basis. And we have seen that such states can be produced using parametric down conversion and so on. But the first experiment that was done in order to show the violation of Bell inequality was not with parametric down conversion. It was in atomic cascade, but it was pretty much the same, that you produce two photons that are entangled in polarization, and using that they were able to show a violation of Bell inequality. So this was in 1981, almost 17 years after this a theoretical work came out. And then this was definitely a very clear proof, but then a better and better violation of Bell inequality was then later reported using photons produced by parametric down conversion. Here is a setup to produce the polarization entangled photon, this one, and then using that people showed the violation of Bell inequality. So this PDC based violation first came in 91, and then in even 2005 there was this work, but people are still continuing with a better and better violation of Bell inequality even now. Okay, so this was a Bell violation or the entanglement verification in the polarization degree of freedom. But we saw that Einstein, Podolsky, Rosen, their arguments were for position momentum, and similarly we could have entanglement in time energy, angular orbital angular momentum, and so on. So can we have a Bell inequality type proof or experiments or entanglement verification done for these variables as well? And the answer is yes. So later people actually showed the Bell inequality violation in two-dimensional state space of even continuous variable. So here is an experiment based on parametric down conversion. So the photons are coming of parametric down conversion, and now one puts these tiny pinholes at 4 locations. And with this, one is choosing, so this is basically choosing the direction of the photon and hence the momentum of the photon. So by putting these slits, one is able to make the two photon state, which is like P1 for signal, P2 for idler, or P2 for signal, P1 for idler. This means if the signal photon goes in this direction with P1, idler goes in this direction with P2, or if the signal photon goes in this direction with P2, idler goes in this direction with P1. So this was the two-dimensional version. This was a state in the momentum basis, but of just this two-dimensional, and with this two-dimensional state people also showed the violation of Bell inequality. Similarly, in this work they made a state which was this is as of 2009, a two-dimensional state in the frequency basis. So first signal is omega 1, idler is omega 2, and then signal is omega 2, idler is omega 1. Again a two-dimensional state in the frequency basis, and using this also people show violation of Bell inequality, and in that case showing the time energy verification of time energy entanglement. And again as of 2009 there was this work that shows that makes this entangled state in the orbital angular momentum basis using this. I will not go through the details of this setup, but essentially the point is one is able to make this a two particle state, which is like if the first particle has orbital angular momentum L1 h bar, second one is L2 h bar, or if the first one is L2 h bar, the second one is L1 h bar. And using this state, then they were able to show the violation of Bell inequality in the orbital angular momentum basis, and thus showing the verification of entanglement in the orbital angular momentum basis as well as the angle basis. So these were the works showing violation of Bell inequality, and now it is pretty much established through all these violations of Bell inequality that the hidden variable interpretation of quantum mechanics is not possible. Although there are still some work that people are still doing and publishing, showing more and more complicated version of hidden variable theories, but again their works in the direction of violation of Bell inequality, better and better violation of Bell inequality, that the hidden variable interpretations are actually not possible. So that's where we will stop today. Thank you.